Greetings. My name is Dylan Meisner. I'm a senior software engineer for Nordstrom Technology. I'm here to talk about our streaming platform based on Apache Kafka and how we're incorporating Flink Stateful Functions as a core component of our event-driven control plane to model and manage the evolving resources in our infrastructure. Nordstrom is a fashion retailer with a physical presence in USA and Canada. Nordstrom Technology supports physical stores and online shopping. We face exciting challenges in many complex problem domains, including merchandising, inventory, warehouse, customer activity, analytics, credit, payments, and more. So why do we need a streaming platform? We've embraced event-driven architectures and near real-time feedback loops across all our domains and systems. Supporting many hundreds of applications and doing this at scale is non-trivial. While different teams are solving problems in their domains in their domain-specific way, the platform facilitates one way to communicate, to replicate data, to publish and consume events. This allows our many domains to be bridged in a standardized way with standardized tooling and frameworks. Infrastructure is hard. We don't want other teams solving these problems. We balance strict availability and durability service level guarantees with keeping the platform growing, evolving, with keeping costs down. We steer the platform in alignment with Nordstrom engineering and security standards in regards to how infrastructure is designed as code, predictably deployed, secured, monitored, and made reliable. Our platform runs as a multi-cluster, multi-region system with a platform interface as a single pane of glass. Resources that teams interact with include Kafka clusters and their topics, Kafka users, user quotas, ACLs and credentials, Kafka Connect connectors and mirror makers, schema registry credentials, Avro schemas, and schema subjects. On a typical working day, we handle over 5,000 distinct changes to these resources. Platform interactions such as searching for topics and schemas, other users, creating topics, connectors, mirror makers, viewing configs, viewing telemetry, and so on. These things begin at our web console or using our REST API, depending on whether you're a human or CI/CD. It's backed by a metadata database. Changes initiated by our users are saved to the database and published as request events. There are also scheduled jobs and long-running workflows, such as credential expirations, that can publish command events. It's our infrastructure that interacts directly with our users' applications. Each region has a control plane, Kafka clusters, Kafka Connect clusters, and a schema registry. Events are received by our control plane applications, and these applications work to fulfill provisioning requests. To light up our single pane of glass with statistics and graphs, we extract telemetry from our infrastructure. We collect from Kafka Broker JMX data, Kafka Broker logs, a Kafka Consumer Group lag monitor, Kafka Connect JMX, and Schema Registry JMX. Prometheus is our core building block for metrics collection and transport. Metrics make their way to our users via a combination of Prometheus federation and remote writing over Kafka topics. Some metrics run through a Flink job that downsamples and adds labels to metrics based on the relationships described in our metadata database. In this platform I've been describing, events originate from the platform interface to arrive at the control plane automation. This automation is stateless. The control plane applications do the provisioning work and emit a result status. Metrics also provide evidence of completed work, and this is a fine model. But the system of record, the metadata database, is distant from the actual infrastructure it's representing. Across these hops, drift has a high probability. And we have some platform behaviors that our scheduled jobs are triggering that must always be executed. If the platform interface is down or the mirroring goes down, we can accept that requests to revision resources will queue up. But expiring credentials, for example, must be removed from the Kafka and Schema registry at the expected time. Moving the system of record to the infrastructure allows clusters to execute behaviors independently. Enter Flink Stateful Functions. As a component of the control plane, our stateful functions can easily perform simple tasks, such as expiring a credential, without needing to be triggered from upstream. When we add in the metrics data, our stateful functions can take on even more complex decision-making. Worth noting, with the stateful functions as the system of record, the object snapshots our function produces can be upsorted directly to our database. Our API services only need to produce the request events, and we can replace our metadata database for a simpler document database or caching setup. Removing our scheduled jobs and massively simplifying our API services, that's very cool. I've thrown these ideas into a simple example Flink Stateful Functions project that you can explore. It describes 3 function ingress: Kafka user request events, Kafkatopic request events, and our metrics data. There are 3 distinct stateful function implementations. One for Kafka topics, another for Kafka users and their credentials, and another for our Prometheus metrics. There are 4 function egress, one each for Kafka topic events, Kafka topic snapshots, which are the materialized Kafka topics at a moment in time, Kafka user events, and Kafka user snapshots. Requesting a new Kafka topic is an event carrying all the information we need to create the Kafka topic and any extra state that we want to be passed through in our snapshots. Adding a Kafka topic means handling a stateful functions invocation. Our Kafkatopic function extends stateful function. It declares the topic state of type Kafka topic. It implements the invoke method for our add Kafka topic requested event. It builds up its copy of the state. It does the hard work of adding a topic, which generates an event. We update our persistent state. Finally, we produce an event and that snapshot of the Kafka topic. We can also handle other lifecycle events like modifying a topic and removing a topic. That persistent state of Kafka topic has all our topic properties, some historical information, and more metadata that'll be useful later on for managing our Kafka topic. Great. So we publish a lifecycle event, Kafka topic added, Kafka topic modified, Kafka topic removed. And we publish our snapshot. And these snapshots are intended to go to a compacted Kafka topic of snapshots that always has the latest copy of the snapshot as the newest value. And if we delete that Kafka topic, a null is dropped into the snapshots topic to represent that it's been deleted. So we've also modeled a Prometheus metrics function. And on that ingress, the metrics look very predictable. They have a name, timestamp, a current value, and 0 or more labels. In this case, we're looking at a Kafka topic messages in rate metric, and the topic that it's measuring is called HelloString. This metric function acts as a router to ensure that metrics that are relevant to certain stateful functions are routed to them. It extends stateful function, declares persistent state. In this case, we're only tracking the value, but we could also track the whole metric. We want the state to disappear if we don't use it very frequently. Often that might mean, in the case of a Kafka topic, that the Kafka topic has been deleted. We don't need to keep the state around forever, so it has a TTL. We implement the stateful function invoke, and if we need to, we can debounce metrics and reduce duplicates, and then we update our persistent state. Finally, we take the name of the metric and we infer if the metric starts with Kafka topic, that it should go to the Kafkatopic function. If it starts with Kafka user, it should go to the Kafka user function, and it's passed. This is how we route to, using that label, we route to the correct instance of the Kafkatopic function or user, and we pass the entire metric. Switching back to the Kafkatopic function, in order to handle two different types of message, we are better off implementing Stateful Match function, which allows us to bind types of messages to handler functions that are strongly typed with that message type. And in this case, when we get that metric, we want to make sure that it's still useful. For instance, I could get a metric to my Kafkatopic function, but if that topic had been deleted, then I wouldn't have any state for it. And this is not uncommon. Coming from Prometheus, I'm gonna see metrics for a topic that's been deleted for quite some time. And then we want to update our state, and we're going to mix these metrics in with the final snapshot that we produce, so that the whole Kafka topic on that snapshot egress topic is sort of the full picture of our Kafka topic. And here is a view of that. The final Kafka topic snapshot includes all of our Kafka topic core data, some extra metadata about when it was created, and other fields that we're passing through here, a delete policy and some tags. The lifecycle status, in this case, it's okay, meaning it's not deleted. It's and then the recent metrics that we're passing through. Lifecycle status really isn't required for this use case, but there are use cases where it's interesting to know if a Kafka topic is in some kind of transition. Yay, it's time for the demo. We will run a Kafka cluster and Prometheus instance so that we can provision infrastructure and get metrics from it. We will create users, credentials, and topics by sending request events. Our stateful functions will create these resources, publish lifecycle events, and publish snapshots. Our stateful functions will also expire that credential that we create, and then we'll tear everything down. Great. I'm in the upper left terminal pane. I have a stateful functions application, and I'll get it going. We want to interact with this function and follow the events that it emits, and also the snapshots that it emits. Great, our function is running. And before I can add a credential, I need to add a user. In this example project, a user acts as an aggregate root for one or more credentials. Our goal is to create credentials with unique usernames that expire, and we want to enable the scenario where a team can have multiple credentials, and as one expires, they could rotate onto a new credential. So we're creating the user, and I already have my new user added event. Notice we've added some quotas here, and I have a corresponding user snapshot. Well, let's create our first credential for that user, and we'll make sure that the credential expires within 1 minute. Great, I have a new unique credential username and a password, and it expires in 60 seconds. I have a corresponding event and a snapshot. Let's add a topic and see if we can list this topic and prove that our credential is working and we're logged in. Great. I've got a hello stream topic that we just created. I'm going to put some data into it, and I'm going to consume it just to make sure it got there. Yes, hello Flink forward. Great, okay, we did a whole bunch of things there. Let's sort of back up here. We added a user, we added a credential that expires in 1 minute, and then we added a topic. And then the snapshots should show this snapshot of our user with credentials added. Here's the identifier and the secret hash. We added our hello stream Kafka topic, and we actually got 2 snapshots. We got more snapshots. The first snapshot coming in was right when we created the topic. The next snapshot shows that it already got some metrics sent to it about the Kafkatopic log size, and because the log size was 0, there's no value here, but we're going to we'll have some more metrics in the near future. Great, and we got our Kafka user snapshot updated. Which I'm not quite sure why it updated. And then the Kafka topic, now it's updated with the log size. And also, so that log size is in the recent metrics block. We also got a rate, and then we got another rate. we're going to keep getting rates because the metrics keep coming in, so it'll keep updating the snapshot. Okay, so now I remember. So this user snapshot here, right here, this came in because our credential expired after 1 minute, and it removed the credential from the user's collection of credentials that we had earlier. Great, so that did work as designed. Demo success. Okay, yep, we're going to keep getting snapshots. Great. And I'm just going to show here that that user can no longer authenticate. We'll get a Kafkacat failure. And great. So I'm going to actually delete that stream, that Kafkatopic. And there's our Kafkatopic removed event. And here now you can see the deleted snapshot, or the null that was sent into the snapshots Kafkatopic for this particular topic. Great. And then I'm going to show something else. You might have noticed the delete policy that we're carrying along on these topics. I'm going to create a topic called Goodbye Stream, and I've given it a 30-second log size delete policy. And you can see that here on the screen. This says wait 30 minutes and for your Kafkatopic, once you detect that its log size is less than, in this case, 1 byte. Great, and once you, so the delete policy says, wait 30 seconds for the log size to be less than 1 byte, and when 30 seconds is up, I want you to delete the Kafkatopic. And I think our 30 seconds is almost up here. And you can see the log size is actually 0, so there it is. We've removed the Kafkatopic. We've got a topic removed event, and we have actually deleted that stream. It's actually gone. We can also remove our user while we're here to clean everything up. So why would you want a Kafkatopic to be to self-delete, to be ephemeral? And actually we have some use cases. We have a lot of topics in our system, and especially in our systems that aren't production systems, they're just forgotten about, laying around, not doing much. But we have a lot of partitions in our infrastructure to represent those topics. It becomes a lot of noise in our platform interface when you're searching. You're seeing test topic 1, 2, 3. So ephemeral topics are useful, especially for developer environments, to keep waste and noise down. There are also cases where we have systems who spin up systems in our infrastructure, not our infrastructure, at Nordstrom Technology, where it's beneficial that they spin up, do some work with the Kafkatopic, and then tear that Kafkatopic down. And if those systems don't clean up after themselves, then we'll just get an accumulation of thousands and thousands of topics, which, again, is noise and waste in our system. So, deleting, having Kafkatopics delete themselves is a really cool behavior that we can unlock. Great. So here is a representation of what we just saw with the delete policy. Here we've got actually 2 delete policies defined, and after 10 days, if the total log size is less than 1 megabyte, or the message's in rate drops to 0, then go ahead and delete that topic. And then the Prometheus metric function is constantly feeding metrics into the Kafkatopic function to help it make those kinds of decisions. So we described credential deletes and then log size delete policy as additional platform behaviors that we can unlock with Flink stateful functions. You can imagine some other useful Kafkatopic delete policies like bytes in dropping to 0, bytes out dropping to 0, or even better, with no consumer groups listening to a topic. The topic migration. People are always asking, "Hey, who's reading my topic? Can I delete it now, or do I need to keep supporting it?" So that kind of information is good to know, and having a delete policy that does it for you is super cool. We also see use for unused Avro schema and schema version delete policies, Kafka Connect create, pause, delete policies, dynamic Kafka connector, and mirror scheduling. For example, having a metadata property on a Kafka topic that says mirror to XYZ cluster automatically for me. The stateful function can get that work going without any further coordination from our scheduled jobs or other systems. Dynamic Kafka quota assignments and tuning. I'm sure all the Kafka users in your clusters are well behaved. So why would we even need such a strange idea? But it could happen. And we also look forward to integrating with cruise control a little much better than we do. For example, cruise control has a wonderful behavior that you can unlock to increase and decrease the replication factor of a topic, which could come in handy when our team has to increase the topic replication factor. It's a very gnarly manual operation that we hate doing. So it might be that this is a great use case for Flink stateful functions as well. Whew. Well, that's the end of our talk. I look forward to all of your questions and ideas and feedback. I want to give a special shout out to the Proton team and all of our Flink friends at Nordstrom and beyond. Thank you.